necessarily. But reminder, if you are sick, it's okay to stay home. The videos should be recorded as long as the audio works. Don't get us all sick. But I know if 30% of you are not here, 30% of you aren't sick unless it's a plague. So attendance is required, but use that responsibly. A few announcements. If anyone's not on the Slack, join the Slack. That is where all announcements are done. If you are not on the Slack, you will miss announcements on homework, rescheduling, and so on. You have to monitor the announcements channel. That is only posts by the TA, Hodder, and I. Is Hodder here? He's back here. So Hodder just got here. Stand up, Hodder. So this is your TA. You don't have to stay for the whole thing, by the way. You can come up here and just wave to people. So Hodder's your TA. We didn't introduce him until today because he was out of town. But he's responsible for any questions you have, any help you need setting up with the tools. I mentioned at the end of last time that there's actually some chip tutorials we have to help you get set up and running on things. He can help you debug if there's issues with those. A good place to start is to ask in the questions channel on our Slack. Search that. We're probably going to get a lot of the same question, and so a lot of times you can speed up the response by seeing that someone else asked the same thing. And that will also help us fix the tutorials if there's things that are obviously wrong. The open source tools change frequently, so things get stale quickly, but we'll try to keep updated, and if there's problems. Do you have any comments, suggestions to people, or?
I mean, it's a fun class, I would say. It's like you're dealing with open source stuff, and a lot of stuff you learn here applies to like if you want to do research or go to like industry, anything. Everything you learn here is pretty relevant.
And I'll say Hodder and I met through some open source stuff. He did tape outs in the open source stuff, and that's how he got into grad school here, right? And same thing with some of my other grad students. So the community is also good. That's another highlight. The tiny tape out community, which we're going to do homework 6 and 7, is crazy good. There's a lot of interesting people on there doing, stuff from high school students to college professors submitting things. And so it's a good mix of people helping out. Okay, now other announcements. Let's see. If you have, this is a big class. As I mentioned, it's 84 seats, and actually we have 81 people right now. I processed some drops because people were not participating with the syllabus quiz, and some people got in off the wait list. I think the wait list goes away tomorrow, but I did document the couple people still on the wait list. I don't know if there'll be any more movement. But what I will say is, I've never made this announcement before, but if anyone has a DRC accommodation for testing, whether it's an individual room, extra time, something, please ask for it. And I'll say please ask for it not only because it's something you need, but it can also help the rest of the students by making more room in this classroom, right? There's a good percentage of students have some sort of accommodation, so take advantage of that. In this class in particular, I often see, I'm having 2 midterms this time. I often see after the first midterm or first couple homeworks, people ask for the DRC accommodations, but request it now if you have it. Number 2, I want to point out, I'm not referring to it every lecture, but there is a full schedule week by week for this entire course that's already up here. It is linked from the syllabus. You should have seen it, the link at least, but I want to point out that it links to this spreadsheet. I will update it if there's any changes, but I expect that it should be roughly this. I have the lecture, the content, the homework due dates, what is on the homework itself, and in Canvas takes priority if I forget to update this. I don't anticipate extensions, but this is a guideline to see how it matches up to the lecture. Some of the stuff on homework 1 I'm going to talk about today and tomorrow even, or Thursday. So they kind of get covered as they're assigned, and you may not know all the answers yet. There's also recommended reading from 2 textbooks. They are both optional, but I highly encourage, if you are going into this field, I don't cover everything you need to know, and these books cover things they will ask you in interviews. As an example, we focus on CMOS logic. There are other logic families. There's pseudo-NMOS logic, there's dynamic logic, but we don't have time in 10 weeks to cover all this material. I've tried to pick and choose to give you the best material to get kind of the most relevant stuff for this class, and then you can look into depth as you need stuff in your career. It's also changing throughout your career, right? Like the stuff I learned early on comes back 20 years later and you have to visit it again. So it recurs. Question?
Is there like we have to read both books or just one of the two?
These are both optional books. You don't have to read either if you don't want to. I encourage you to look at them, but they are optional. If you don't understand something in lecture, you can rewatch the video in lecture, or you can go visit these books. Sometimes I'll give an entire lecture on something that's 2 pages in this book. Other times the book will have 20 pages and I'll mention it in one slide. So there are some differences. The lectures are the most important thing, and you should be able to do the homeworks by just watching the lectures. But I want to just put that there because a lot of people are like, oh, there's no book. There is a book. It's just different than what I have. And as I mentioned before, there are no good books because people don't get paid to write them, and technology changes. And so there's not one good book that I can say, read this and it's good. So that's why I give you some selections and so on. Yes?
So do you think one book is just better than the other?
No. The classic one is the left one, but I actually think the right one may be more accessible and a little more up to date, but not really. Okay. And then I will have 2 other readings that are not in the book that I'll put in Canvas. These are PDFs you can download from Canvas, because neither book covers those 2 things in enough depth. Yes?
Regarding the wait list, so you said it closes tomorrow. Is that?
No wait list questions. Come talk to me later.
Okay.
Sorry, we don't have time.
No.
So, yeah. Yeah, I didn't mean to cut you off, but
Yeah.
I've done this class for 20 years, and I have it kind of precise on what I want to cover. Syllabus quiz. This is Mina. So that's my dog. This is my other dog, Gozer. Does anyone know where Gozer, the name, comes from? Gozer the Gozerian, the chosen one. The original Ghostbusters. That's her chosen form. So I'm a fan of Ghostbusters. So let's see. I had one slide to finish up on the last lecture. And that was a step of planarization. So I talked about, what were the other steps I talked about? I talked about photolithography. I talked about, what were some of the process steps? Oxidation, etching, implantation, deposition. That's basically the main ones. And then they're all in this photolithography process, right? Until the 80s, what happened was you only had processes with, say, 3 metal layers, maybe even 4 metal layers. And the problem was every time you add a layer, you're adding a layer on top of another layer that may be uneven on the wafer. This unevenness accumulates as you go up in the chip stack, and pretty much you end up with a topography on the chip that means when you put a material down, it ends up being thinner in some spots and thicker in others. And so they were limited in how many metal layers they had, until they realized they could do this step called planarization. And what this is, there's one that's called chemical mechanical polishing. There's actually a newer one called electrochemical mechanical polishing, which adds some charge bias into it. But literally what this is it's a polishing step where you have a, if this thing on the right over here is your wafer that we saw, you basically have a kind of little pad with an abrasive on it. It's basically sandpaper, very, very fine-grained sandpaper. That thing rotates, and you also kind of move it around the wafer at the same time. So the idea is it's moving in multiple directions to uniformly erase and even out the chip. The wafer. And if you see, for example, if you have features, like this could be metal here, this could be polysilicon, this could be any feature you put on there and etched away. And if you put the next layer on, you see kind of the oxide that might grow over this that's uneven. So this is supposed to fix this, where you can polish this down, but then you end up with thinner areas here, then over here, and so on. Why do I tell you about this stuff? Well, when you do design, you may have to do things like add extra metal shapes that are not there for electrical reasons. They're there for mechanical reasons for manufacturing. Here, you might have to put in dummy metal in this spot just so you don't have this blank area that can cause this kind of dishing effect, because this pad ends up having some flex to it. It doesn't polish perfectly even. And to counteract that, you add dummy metal in here that you get much more even. They will add metal density requirements on your design so that you have an uniform distribution of density due to some constraints. This is the type of thing where, I mean, as a designer, you come in and you're like, why am I adding this useless wire here? Well, it's for this, right? And so there's these things that come back into play as designers where you have to do them. Now, this is bad because we'll later learn this can actually change the electrical behavior of this because it may be a wire that's close and adds capacitance. So you have to add it for manufacturing, but then it also affects your performance. And so you have to consider it during design. So that's kind of a looking forward into the class. You know, a lot of these things, you need to have some sort of understanding of the fundamental materials and fabrication that you then can use as a designer moving forward. So this is basically a typical CMOS process, and this goes through the steps that I talked about before. I'm actually going to talk about this more when I talk about the masks, and that's mostly what I'm going to talk about today. So I'm going to kind of gloss over this, and we'll see it a little bit more later. And I already showed the layers the previous class. So I'm going to now move on to the layout lecture. Oop. Sorry. There we go. So any questions so far? We good? Okay, today's lecture, we're going to talk about layout, and this is basically creating the shapes that get turned into the masks that get then used for those manufacturing steps. And then the lecture after that, I'm going to talk about devices, so how these layers actually create the silicon devices and the interconnect on chip. So these are the next two lectures. Now, I always get questions, what do I expect you to know from these lectures? How do I test you on these lectures? Well, we'll post homework 2 coming up, where you're going to have to do some recognition of layout and kind of reading of the mass to understand what it is. Once you get exposed to it, you can look at stuff and pretty much tell what's going on. You know, without kind of learning what it is, it looks a lot like an abstract painting with a bunch of colors and shapes and so on, but it has definite meanings, and they're very similar from process technology to process technology. You learn one, and what the same colors and kind of usage of shapes applies to the next one, for the most part. So it's very useful. And then we're going to talk about the design rules. So this is basically certain conditions or relations between shapes that you have to do to make sure that the manufacturing can be done correctly. And then we'll get into actual transistor layout. And if I have time, I'll do a K-layout demo. I brought my laptop too because iPad's not so great with that. But we'll see how much time we have for that. Now, pop quiz. Okay, everyone take out some notes. No, I'm just kidding. The question, how can you do well in this class? Does anyone know? Anyone? Yeah. You must do the homework on your own and try it beforehand. Yes. You have to do that. So I told you I'm going to talk about this every time. You can keep your solution to yourself. You can check what we just did. Don't just look at the answers. Go through and do the homework. Okay? That's all I'm going to say about it today. I've announced this every class, Hodder, so. Now, so these design rules. So a way to think about these, it's a contract between the people that manufacture your chip and the designers. And what it says is that the people that manufacture the chip, say whether it's TSMC in Taiwan or Global Foundries in upstate New York or whatever manufacturer, they want to be able to say, okay, you gave me something, I can make what you gave me. And it's also a way for the designer to say, okay, I followed your rules, what you make should work. Now, what does it mean work? Well, it may not meet electrical timing and stuff, so logically it could be wrong. Electrically, it could be wrong, but it will be manufactured as you gave it to them. And the devices, if it's a transistor, it'll be a transistor. If things are connected, it'll be connected. So it'll be physically there, but the other verification steps are up to the designer, and they won't guarantee it. Another way to think about it is the people that manufacture it have no idea what your chip does. You gave them a bunch of shapes, and they make those shapes into a physical thing that hopefully works. The designer knows what it does and knows why they're making those shapes. So this is kind of this pass-off between design and manufacturing. Now, there's some softness in there where design rules, traditionally there's some design rules that are yes, no, like you have to do this or it won't work. But in reality, the design rule is kind of a guideline where if you follow this rule, it will likely work. There may be extreme cases where it doesn't work. I think I asked before, who's done PC board design in here? A few people. How wide do you have to make a wire in a PC board design?
However wide the manufacturer says.
However wide the manufacturer says. Typically, you can kind of violate it and say, oh, I'll make it narrower, but they might say, oh, the board might not work, right? They don't necessarily check that you did everything, but it's variable. The same thing kind of applies for design rules, but they'll give you a set, and there's a set of rules that you have to follow. If you're a high-paying customer, let's say you are Apple and you're working with TSMC, and you may say, oh, I keep running into this design rule. Is there any way you can give me a little leeway? TSMC might say, oh, yes, thank you, Tim Cook. We'll give you some leeway, give us more money. Not really. They'll have some leeway there where they can have what's called a design rule waiver, but those might be extreme, rare situations where they might have a compromise. But in general, these rules are yes, no. Now, what are they? Well, you're going to have, in general, two sets of design rules. And this is where the books are kind of wonky. One of the original books, that Rabe book, and some of the older books talk about what's called a scalable design rule. And the idea here is you have some parameter lambda, and then this is your half of your minimal printable feature on a chip. And you make every design rule a multiple of that. And then you can say, oh, if I move from one technology to another, if I just scale this one parameter, it might scale up the layout linearly. That doesn't work. Like, it has not worked since the 80s. The reason is the different dimensions and the different rules don't scale linearly. They all scale for different physical reasons, and they change in every technology. The books talk mostly about these. That's why they're outdated. Instead, what most manufacturers use is absolute rules or micron rules, where they'll say, these two things have to be separated by 0.4 micron or 400 nanometer. They're typically units in microns or nanometers, because that's kind of the scale we're looking at. So they're going to be a set of rules that are usually in absolute dimensions, and then it's going to include a set of layers. So these different they might correspond to a mask, but they're going to correspond to a layer you draw. And that layer you draw can be converted into a mask. It's not a one-to-one. I'll talk a little bit about that later. Then you have a set of rules where you can have intra-layer and inter-layer rules. So intra-layer rules are basically rules between, say, two metal wire shapes on the same layer. They have to be spaced apart or something. Or inter-layer, where you have two shapes on different layers and they have to interact in some way. So you have rules for both of those cases. So what does this look like? And why do we have these design rules? So at a high level, it's to tolerate manufacturing variation. They manufacture these chips. They go through the lithography process. They do an etching. You can misalign that mask. It's a physical machine that zooms down with the imaging, and it may be off by a small amount. You could have, and actually right here on the right, this shows two masks that might be used, and here's a set of crosshairs. They'll typically put extra features on the mask to help you line them up, right? A crosshair will give you like X, Y, and rotation. Kind of like when you fly, you have your yaw when you're a pilot, which is another kind of rotation. So you have this with the masks as well. And you can see those two shapes, you want them to overlap because maybe they're metal, the same metal layer that's supposed to connect, but in vertical and horizontal maybe. Or it might be metal 1 and metal 2, and they have to be lined up. That's a better way of thinking about it. You could have dust particles, right? If you have a piece of dust that gets in the way of your photoresist either depositing on the wafer or the light exposing the photoresist, it could cause either an absence of a shape or an extra shape. You know, if it's stopping an etch, it'll leave something there that it's not supposed to. Or if it's blocking something from being deposited, it will have something gone that's not there. So it can be either a positive or negative kind of defect in your layout. You can have things related to the process steps. You know, here is an example, and we haven't talked about it yet, but this source and drain may be implanted with an implantation step. But then remember I mentioned when you kind of shoot the ions into the surface, it roughs up the surface. You then have to heat it up to smooth out the surface of the silicon again. Well, when you heat it up, those ions you implanted diffuse in all dimensions. And so you may end up with slight undercutting here, where you can see on this edge that it goes underneath that other layer a little bit, which you didn't intend to. You may have drawn it so that it perfectly lines up, but it isn't. Or on this side as well. So that can cause problems. Or as I mentioned, we talked about CMP, where we try to make it flat. It's still not perfectly flat after CMP, but you can have rough surfaces of metal with some density difference, and there's a tolerance to that. So they may say that you have to have, what's an example? If you have, for example, one case, if you have very wide metal wires, let's say for a power distribution, you can't have a wire that's a certain width. Instead, you have to insert slots in the middle, kind of excerpts, to make sure that you have the opposite of metal, so oxide, to make it easier to polish. So that might get rid of a rough surface. Or you might have size rules related to that, to the topologies. All right, so these are just some examples of why we have the design rules, but it's basically to tolerate these different kind of mismatches. Now, here's the diagram I showed at the end of last lecture, and we're going to talk about how roughly the masks correspond to the different process steps. But I want to point out that this is a simplified 12-step CMOS process. The modern processes use more like 60, 70 masks, and they're more complicated. Now, you may ask me, oh, what do you mean by more complicated? Why more complicated? What features do we add? Well, here's an example. When you print metal, you may say, oh, how many masks do you need for metal? Just one. I have metal 1. Well, what they'll do is they might do a process step that's actually called, they might have multiple exposure masks. And what happens is when you're doing this exposure step, your wavelength is actually in one direction. And so if your wavelength is in one direction, it goes through a mask better, say, horizontally than vertically. Like, think about polarized glasses, right? You wear these, if you ever have a computer screen and you rotate it, you can find that point where you can't see your computer screen. What happens is the light coming out of your computer monitor is polarized, and your lens is oriented in a way that it can't penetrate. Now, what if you want the light to go through your mask? Well, your mask, if you have a bunch of wire shapes, they're typically all going in one direction on one layer, and they alternate on each layer. Metal 1 will be one direction, metal 2 be the other, and so on. It's kind of this Manhattan orientation to help routing. So what happens if your light on one layer, all your shapes are going one direction, and let me back up. Let me say on metal 1 you have some shapes that are going horizontal and some are vertical. Well, if the light is polarized in one direction, it will only go through the horizontal shapes. So what do? Well, you make 2 masks. You have one that's horizontal, one that's vertical, and you do 2 photolithographic steps to do the same shapes, right? That's to get one patterning and one set of metal. Now, that's one example. That's kind of a contrived example. A better example is let's say you even have a bunch of, it's a little bit of a tangent, but I think it's good to talk about why there's so many masks. Let's say you even have a bunch of metal wires that are in parallel, which are like your polysilicon we're going to use to make our gates. Well, another example of dual exposure or double masking is instead of having every mask or every poly, you'll actually have every other poly. And then the second mask will have the odd poly. Like one will have the even, one will have the odd. Why? Well, even when you do have polarized light go through this, there's this idea of diffraction. The light kind of changes direction when it goes through and spreads out. So if you have two shapes next to each other, if you put light through this one and this one, they interfere in the middle. They could interfere positively or negatively, but they'll change your layout that gets exposed. So what do? You split them, and you do them one at a time so there's no interference from these nearby shapes. That type of thing can be extended to double exposure masks, triple, even quadruple exposure masks, right? So you can have 4 masks that actually get printed for one shape. So many more masks, but this is basically a standard CMOS process and kind of gives you the idea of the steps and how they create the devices. Now, the general process, first step, you start with your wafer. In this case, it's saying it's a P-type substrate. It could be N-type, but P-type's common. You generally grow a field oxide, which is just you oxidize the whole thing and you etch away part. Now, why is this called a field oxide? Well, this is going to define anywhere you have an active device versus a non-active device. So right here, this kind of region right here is going to specify this as the active region because I've gotten rid of that oxide right here. Actually, that's not quite right. That's good enough. Now, what this first one does is basically lets you define not the active area, but the well area, I'm sorry. And so what this does is here you can basically open this area and you do one implant step. Now, this says diffusion. Remember, diffusion and implantation are both ways of adding dopant materials to the semiconductor. You can make it P-type or N-type, depending on if you add boron, arsenic, or phosphorus. So what we started with a P-type substrate, we opened up this area that's going to be what we call an N-well. Why do we call it a well? I actually don't know. That's what they call it. But it's basically an area that you add enough of the dopant. So the P-type's going to have, I always confuse which is which, but P-type I think is phosphorus, and then you're going to add the opposite type, boron, I could have them swapped, to this material such that the boron, let's say, outnumbers the P-type and basically changes the type of silicon. It's a cumulative effect. Because remember, if you're adding one type of dopant, you're adding an electron. If you're adding the other type, you're adding a hole or an absence of an electron. So if you add an electron and an absence, they kind of cancel ech other out. Yeah?
When building a CMOS, do you need to know the elements that you're using?
That's a good question. Do you need to know the exact elements? No. But you do need to know the type. That's why I don't know the elements. And it could change as well, right? I don't know if they use arsenic or phosphorus. I have no idea. In terms of, I mentioned the other processes for like space stuff, they have the gallium arsenide processes that use germanium. That uses gallium and arsenide. They're still P and N, right? But different materials. So in this case, you implant that N-type thing that causes an N-well. Now what this does is it gives you now certain areas that are P-type, and then in the well areas, they're N-type. This is going to be useful because we're going to make different types of transistors in the different wells. Looking forward, you're going to use the P-type substrate area to make NMOS transistors, and then the N-type material to make, other way around. The P-type area to make PMOS transistors, and then the N-type to make the PMOS transistors. I had it right the first time. And so you can see here, you create the well. Now this is the active area etch. So here you can open up this area to open up this for the NMOS in this area. Then you have another step where this oxide was a thick oxide. It defined where I don't want transistors. I need to actually grow a very thin oxide. And this thin oxide is highly controlled because it's going to be the gate oxide for your transistor. And it's highly controlled because it determines the threshold voltage and how your transistor electrically behaves. So now you grow this gate oxide. It's going to be the same process as the other oxidation step, except slower and with more accurate control over the process. And this grows the oxide for both those devices. Now, you put P-type polysilicon over the whole thing, okay? And then you go through and you etch where I don't want polysilicon. In this case, polysilicon is going to be used for the gate electrode of the transistors. Again, I'm going to talk about devices next lecture. We'll spend the whole time on it, but just assume that I'm talking about the transistors here. And you can see here, you're left with essentially these two areas that have polysilicon as well as the very thin oxide underneath it. So that polysilicon is electrically insulated from the area below, which is going to be called the channel of the transistor. Then we do two more steps here. One, we do another implantation step, one of N-type and one of P-type. And what happens is, you can see in here, in this red here is called P+, and it's in an N well. Whereas this material over here is N+ in a P substrate. What was the plus minus again? It just means highly concentrated, whereas just N or P is just regular concentrated. Again, you can have negative, which means lightly concentrated too. So now, these two steps form the source and drain of the transistor. Those two blue things are the source and drain of the NMOS. Those two red things are the source and drain of the PMOS. And then you have the green gate electrode on the top. Yes?
What could happen if one of the steps was missing when you're building?
If one of those steps is missing, well, the designer would be asking for a refund. But yeah, you just wouldn't have the transistors. Yeah. Yeah, it would be basically a gate electrode that's a conductive, and then nothing that could conduct between to make a switch. So after we have that, we then grow another nitride layer, which is kind of, it's like an oxide. It's also an insulator. We can etch the nitride, and notice here, we want to etch it in a way that there's actually a pathway down to these source and drains. We etched vias or contacts, holes, so we can then fill those with metal to make contact between the N+ and P+ and this other metal material that's going to be on the next layer. Question?
What's the point of nitride specifically as opposed to just more oxide?
Yeah, nitride and oxide, they're both insulators. I think it's a good question. I don't have a good answer. Yeah. Sometimes you end up with different interactions between materials, and so it might be that. But yeah, I don't have a good answer. Yes?
So is the N+ and P+ on the left source and the one on the right drain? Or is it the gap specifies what source and drain is?
Let's pause the source and drain and so on till the devices lecture.
Okay.
Yeah, next time. Because I want to talk mostly about just this layout and how it translates to these. But I guess a rule of thumb is the source always depends on how you use it. So these are actually symmetric devices, right? Right now, you don't know which is which. You can take a MOSFET, and if you flip it, it'll have the same exact behavior. And so until we hook it up in a gate, we don't know which is the source and drain. Now, when you hook it up in a gate, generally the source is connected to the supply side. So like for a PMOS, it's connected to VDD, or the transistor connected to VDD. And if it's an NMOS, the source is connected to ground, or the transistor connected to ground. And then the drains are connected to the output of the gate. We'll see. But yeah, so then you might put down nitride or oxide, and then you deposit metal, and then you etch away where you don't want metal. So here you have a connection from N+ through this contact to the metal wire that may be your ground wire. over here, this P plus is now connected through a contact hole up through to this metal, which is connected to, say, your supply. And then you have two gate electrodes that are connected to polysilicon that are the input that'll get routed together on another layer if you want an inverter. Or in this case, the drains, like you were just asking, are connected together for this P plus and N plus, like through these connections. So this is the start of an inverter, except we don't have the gates connected yet. You have a separate input for the PMOS and NMOS. Now, what are the general layers in a CMOS process? Well, I'm going to caveat this that this is a bulk CMOS process. So what that means is we start with a P-type. We may not always have a P-type wafer. In modern processes, a lot of times it'll be on a wafer that is basically, it is silicon, but then you actually grow an insulator over the whole thing, and then you do what's called silicon on insulator. So in that case, you might be adding wells on top of an insulator, and it's a little bit different than what we've shown. But you generally have layers for drawing P well and N well, whereas this process, everything started with P, but we might actually have a layer that says, oh, make another, if this is insulator, make a P well here. Okay, so that's why sometimes you draw both. Actually, a lot of times you'll draw both. You'll typically have a layer called diffusion. Another way, it's also called the active area. This is where we're going to have active transistors. We're going to have polysilicon, which is a conductor, but it's not metal. It's not aluminum or copper, but it's still a conductor. Wherever that overlaps with the active area, you end up having a transistor. You end up a lot of times drawing a P plus and N plus. This is where the source and drains go. And then you start getting into the interconnect stack where you have contacts or vias. These are different names for basically the same thing, but they're holes through a layer where you can have conductive material. That's either tungsten or metal or something like that. And then you have, these can either make connection to the diffusion or up to poly or between different metal layers, right? You can have a via 1 between metal 1 and metal 2 and so on. And then those then obviously all the names, metal 1, metal 2. Some processes have a layer below metal 1 here called Li, or the local interconnect layer. I don't know why they don't just call it metal 1. They call it local interconnect. Yeah.
Do the PMOS and NMOS share the same bulk, or?
Yes, the PMOS and NMOS both share the same bulk. In this case, this P substrate is the bulk. That's another way of saying it. Actually, I think I might know what you're asking, and I'm going to talk about that more. But they're both manufactured on the same substrate. I'll leave it at that for right now. All right, so these are the typical layers that you have. Now, how are they drawn? And so this is where learning one technology, you generally applies to all technologies. This is the 0.25 micron process in the book. This is not similar, not exactly like the one we're using, but generally you have certain colors that are used for certain shapes. As an example, polysilicon is almost always red. Why? No idea. But conventionally, every time I've done layout, it's been red, except at, I think Intel has it as green. I don't know, it's just how you set it up. You could change this color scheme to anything you want in the tool, and it has the same function, because it depends on how you save these and give them to the fab. They care about what it's actually a layered number in the file format that corresponds to what they look for. Right? This is just for display purposes. Almost always metal 1 is blue, and metal 2 is some sort of purple. Beyond that, it can vary quite a bit. You can see they also do things like add like hash marks and stitching and all sorts of patterns. These are the contacts. They're almost always just black, and so they're hard to differentiate sometimes, black or gray. N-well is almost always green or a tan. Diffusion is almost always green. usually N plus and P plus, since these are similar to those diffusions that are made for the well, they're kind of, checkerboard patterns of a similar color usually. So, right, because it's, high density, medium density, so you'd use this more, so it's usually more opaque, so it's easier to view than this one. But this is generally what happens. And I'm going to kind of skip over this because we don't use the process in the book. Instead, we're using the Skywater process. And here you can see almost the exact same thing. And again, I put this layer stack that we showed before. And here you can see, again, polysilicon is also red. That's the standard color. Diffusion is green. And if we draw these, so this polysilicon corresponds to this and this. The diffusion here corresponds to this down here. And metal 1 here corresponds to this. And metal 1 again is blue. And you can see, in this case, the via, they made it a shade of blue. So it's not black, but it's a different shade of blue. Now this is the example of why the color doesn't matter. And see, this is actually a view from K-Layout. This is the tool we use in this class. This kind of is a layer palette, and it's almost identical to the commercial tools you might use, say Cadence and Virtuoso. And the thing you can see in here that is important for the fab is this second thing, these two numbers here. This is called a layer purpose pair. Now, what is a layer purpose pair? The layer corresponds to what mask gets generated, right? And here you can see metal 1. Well, all the metal 1s are 68. 68, 68, 68, 68. If you draw a metal 1 pin or this drawing shape or this label, this pin, or this, these are all the same layer of the mask, and they get the union of the geometric union of those shapes gets put on a mask. They get ORed together, right? If you have a pin and a drawing, they're both shapes on the mask. The label is text. That actually doesn't get drawn in the mask. That's used for convenience, but it puts it on a layer so you know it's related to those metal shapes. Now the second number is the purpose, right? You notice the metal 1 drawing layer, this is for general wires, is 20, whereas the metal 1 pin is layer 5, and the label is 16. That's telling it what you're using that shape for, right? A pin layer is something you're going to connect to when you have like a cell and you have an input and output. Those are the parts of the wire you want to connect to. So you can tell it at the next level up where the connections should be made. It gets manufactured still as metal, but it has a different purpose in the layout. Question?
So I noticed that on the metal ones, the pin is /5, the second purpose. Up above, the pin is /16, which is the label for metal 1.
Yeah.
So are the numbers like standardized across?
So these numbers are not standardized. It's basically whatever the fab tells you. They say when you save this file, you're going to end up saving all this layout in this format I said it was GDS2 or GDS, Graphics Display Systems 2. It's a 1970s plotter format. Each of these layers gets put out as a different layer that they then say, we're going to look for 68, purpose 20 and 5, and we're going to turn that into the mask. You can make it green, you can make it purple. It's going to save to these layers, and that's what they're going to look at. So if you give them a different numbering, they're going to complain. They're going to be like, you have no metal on here. And so yeah, it's in the what's called the process design kit, or the format they tell you to give it to them. How do they decide it? I don't know. Yeah, why did they pick 5 for pins for that and 16 for pins for the poly? No idea. Yeah, it actually looks like it might have been even almost someone who's a little dyslexic, right? Swap it for these, but not for these. I don't know. Yeah.
So the Sky 130 thing, like kind of like a semiconductor, and the diagram that's shown over here is how it's like layered
So Sky 130 is the technology node. So SkyWater is the manufacturer in Minnesota, Bloomington, Minnesota. This is kind of just the layer stack that they gave you for relative dimensions of things, just as an FYI. And then these are the layers in the tools that you use to draw the masks that can then manufacture the thing on the left or other layout.
So when we talk about layers, is it like the layers of a specific physical thing, or sorry, how do I put this? Like, is this like
I think I understand what you're going to ask, and it'll become more clear when I start talking about how we use the layout. So I'm going to get to some more slides that I think will clear it up. Yeah.
Might be unrelated question, but does SkyWater 130 only has 5 layers, or could it have?
Yes, it's only 5 metal layers and an RDL layer. Remember I talked about last time that layer that helps you with the redistribution for the chip on board and so on. So technically 6. Actually, there's also technically the LI layer, local interconnect. So this one right here is the LI layer, and then there's metal 1, and they don't show the RDL layer here. This one, though, they generally don't call it a general metal layer because it's actually very high resistance, and they say don't use it beyond a single logic gate because it's a bad wire, basically. But they can print it very small. So it's kind of 7 layers. And then you might add poly in there too. Poly is technically a conductor. Yeah.
Why is each metal layer thicker?
Why is each metal layer thicker? I'll talk about this when I talk about interconnect. It comes down to how much resistance it has. Thicker means less resistance. Now, here's another example of a process. This is a 45 nanometer process that I used to use in the class before the open source stuff. And on the right here, you see actually a screen grab from Cadence Virtuoso. And you can see basically the same thing I just showed you. This one has slightly different shapes. You still have P-well, N-well, you have active, poly, contact metals. There's a couple extra layers, and they have the similar colors too. You know, poly is red, active is green, and so on. There's a couple extra mask layers here. For example, in this one, you can actually have VTG and VTH. Those are actually extra layers, so you can say, I want this transistor to have a regular threshold voltage and this one to have a high threshold voltage. The high threshold voltage will end up having bigger delay but less leakage power. And so you may want to use that in some cases. And it's an extra mask, and it basically surrounds which transistors you want to have which threshold. I'll talk about this a little bit when I talk about devices. Similarly, this thick oxide, generally when you have, remember we drew the I/O perimeter cells around the chip? Those interface with the real world, and they usually have higher voltages. To use those, you can't hook those up. You can't hook external things up directly to the transistors we make because that oxide is so thin that any sort of electrostatic discharge or high voltage will actually just blow through it like a fuse. So you typically have thicker oxide transistors. So underneath the polysilicon gate is thicker so that it can handle higher voltages, maybe like a 3.3 volt or a 5 volt voltage. Whereas your other oxide may only be able to handle up to like 1.2 volts or even 1.8, somewhere in that region. So you may have to draw this and say, oh, this is going to be a transistor that's in my I/O area and it's used for the interface stuff. All right, so you can have extra layers for extra things. In a lot of processes, you end up with many layers you don't use as a designer, as a digital designer, but they can be for other things. These ones you may use. Now, let's talk a little bit about the operation of the transistor. Enough for this thing, so we talk about source drain. So in general, we have 3 terminals to a transistor. We have the gate electrode, the source, and drain. And you should have seen in like CSE 12 and 100 and 125 kind of the basic switch model, right? If it's open, there's no connection. We're going to augment that and say when it's closed, it's basically a resistor. It's no longer a perfect connection, but there is some kind of inhibitance to the conduction of electric. This is a first order transistor model. And it's better for first order analysis, and I think it gets you kind of 85% of the way there for what you have to do as a digital designer in most cases. Now in this case, when it's closed, we saw this side view before where we had the polysilicon, we had the gate oxide, the field oxide. This is labeled as B. This is either the bulk from the substrate from the wafer, so the P-type, or if it's the other type of transistor, this could be the well. Like if we're making a PMOS device in the well, this could be that well. So it'd be down here, that I'm just not drawing it. But generally what happens is when it's off, you have source and drain like this, but when you apply a voltage to the gate, there's a difference between the gate and source of a substantial amount, what happens is you form a channel in the region under the gate, which remember when we have silicon, we talked about the holes and electrons, right? And we talked about adding dopants so that you have electrons or holes. Now, if you apply enough voltage, what is a voltage? It's going to be electrons. Now, what happens if you have electrons and then underneath that oxide you have electrons floating around? What happens with like charges? They repel each other. Opposites attract, like charges repel. If you put enough electrons here, it's going to push the electrons here away. That's going to make this basically filled with holes, which will then connect this. Same thing for a PMOS, except a PMOS, you're going to put holes on here, absence of electrons, and it's going to push away the holes here and make electrons here so that you connect. That way, kind of imagining these two carriers, because remember the holes are not really a carrier, it's the absence of the carrier. Imagining these as two carriers, you get two types of devices. The NMOS will close when you apply a voltage, whereas the PMOS will close when you put the negative voltage on there. You take away the charges and create the holes. So that's why there's essentially a free inversion on the PMOSs. But when it is on, though, if you think about it, this region underneath here has some physical shape. That's what determines this voltage. And how many electrons can flow through there or holes can flow through there depends on how much area there is in that channel region that's created for it to flow through. The more voltage you apply on the gate, generally the bigger the channel gets until it hits a certain point called saturation where it can't get any bigger. Now, I'll talk more about that later, but that's kind of the gist of it. I wanted you to get the overall kind of high level. Now, how do we start making these out of the layout? Well, first, the intra-layer rules. So this is within one layer. In general, you're going to have two rules. One is a kind of a minimum dimension rule. This is how wide or long something can be. And this is usually for wires, let's say. It's how the minimum width to make sure that you can print it reliably. It's usually set by the photolithography process, and it may depend a little bit on the topology and the polishing and how uneven things get and so on, but it's generally based on the printing. Then you also have a space between objects, and that generally depends on whether you could have a defect that could cause, say, metal between these to not be etched away, that you would have a short circuit. So it's, again, kind of related to the contaminants. The width can also be related to contaminants, too. If you have something very fine, a single dust particle may prevent metal from being printed and prevent the connection. So here's an example, an excerpt actually from our design rules. These are all available online, and we can have links to them. And you'll have design rules in any process that are usually numbered with, for example, M1, that's the layer, dot 1. This is design rule 1, which in this, it's convention. Most processes have similar numbers. This is the width of metal 1, which says it must be at least 0.14 microns. M1.2 in Skywater and a lot of other processes, this is the spacing rule. The spacing of metal 1 to metal 1 must also be 0.14 microns. So the width and spacing are the same. Now, as an example, you could have, this is metal here. This example here has a via 1 or via 2. In these cases, you might also have rules that say instead of a minimum width of the metal, a via 1 might say you have to have the width of the via be exactly this. And I forget what the rule is, but it's like 0.05. You must have a width and height of a via of 0.05 exactly, no bigger, no less. Now why? Well, when we etch those holes, it's a very sensitive to kind of the area and how much of the etching acid can get down in the hole. And so you want to make sure that that ratio of the size and the concentration can etch away the material. If you suddenly have big vias and small vias, it's going to etch at different rates, and you're going to have some holes that go all the way through the layer and some that don't. So for that reason, they say that there's a limit on the size of it. If you want a better connection, what you instead have to do then is have more than one via kind of spread out. You might have a 4x4 array of vias to make a better connection. But every one of those 4 vias is the exact dimensions that you're told. So it could be minimum dimensions, it could be exact dimensions, and then you might have spacings. The via spacing is a minimum separation. It's not an exact separation. So this is kind of a within layer. And this might apply to via 1 and via 2. That's just an example. So some more intra-layer rules. You might have layers between polysilicon. Poly.2 is the spacing of polysilicon. Poly.1, it actually in that case has some sub-rules. There's going to be poly 1.A and 1.B, or .1b. That depends how you're using the polysilicon. I'm kind of skipping over it here. The N well, this is that well we create so we can make the PMOS devices. You're going to have a minimum width, and that minimum width will apply to all the sides. But in this case, you might want to make something that's not just a rectangle. You're going to have a spacing rule here, like metal 2.A, which says this is basically a notch spacing. If I have something in here, this is the same N well. This spacing can actually be a little bit less than this NWell.2A, which is the N well to another N well. Why? Well, if this gets short-circuited, it might not be so bad because it's the same shape. If this gets short-circuited, that could be bad, it would be destructive. So there's a kind of a function with those design rules there. And then I replicate the metal stuff over there on the right and the via stuff. By the way, this right here is white, but that's not absence, that's just the label that got kind of screwed up. So now, the interlayer rules. So this is between different layers. The most important one is pretty much the polysilicon in the diffusion area. And again, that's red and green in these cases. In this case, when you draw the poly, this diffusion area is going to end up being the source and drain, right? Source, drain, and then again, this is the gate. Now we want that poly to fully overlap the diffusion. Now, I should note that this is one single shape, right? It goes under here, and you just can't see it because it's kind of overlapped. If I draw it in green, there's green under there too. But these things are layered. And so it's kind of obstructed from your view. And so what happens when you form this gate? Well, you do the implantation step of the source and drain, and it doesn't implant where the polysilicon is, because this is what's called a self-aligned gate. So that polysilicon says, oh, don't implant there, so there's this channel that gets then modulated with the electrical charge, right? Now, here we have a couple design rules, because if we have mask misalignment, for example, these are two different masks, right? We do one for the diffusion step and then one for the poly. Whereas here, generally these were the same masks unless we do multi-patterning. But this is one metal one mask, one NWEL mask. In this case, there's two different mask steps which can have some misalignment. And we have to make sure in this case that, for example, there's a minimum extension. Let me draw it in. This is basically a minimum extension beyond. So this is poly minimum extension beyond diffusion. And you say, oh, it has to extend beyond because if there is a misalignment, we want to make sure that what's on the right doesn't happen. Because if we had a slight misalignment and it didn't extend far enough, there'd be a diffusion where the source and drain are actually connected with a bit of P plus or N plus. That is something that, rather than being a transistor, it's basically a transistor in parallel with a resistor. Right? This kind of sneak path around the edge of the poly is always connected. And then depending on if we have a voltage on that, the red poly gate or not, it'll either be connected under the red or not. So it'll be more connected if there's a voltage and less connected if there's not. So that's horrible. Now, similarly, so this is where we actually want to form a transistor. Down here, what if we don't want a transistor? We can have some diffusion and we can have some poly. Both of these are actually conductors on their own. This can electrically conduct, this can electrically conduct. You should not use them as wires except within a gate because they're highly resistive. They're bad wires, but they're wires. And by wires, I mean electrically conductive. They're not made of metal, right? Again, this is polysilicon, and this is either N plus or P plus, but they're both conductive. And so if we end up routing something for some reason on this metal and this diffusion, we don't want them to overlap because now we wanted this to be connected, but now the resistance depends on whether there's a voltage here or not. So we'll get this weird behavior of the behavior changes depending on your input pattern to something. So that's bad, which we basically made the same thing as the above, except the other way. We didn't want any transistor. We suddenly got this kind of partial transistor. So this is an example of kind of the most important rules. You notice here we have the extension here. We might have an extension rule here. Both of these layers also have the width and spacing rules, right, that we talked about before, the intra-layer rules. Questions so far? No? Now I like to show these because that's kind of a cartoon. This is actually what you get from the manual again and kind of diagrams. Now, I show you this because part of being a VLSI designer is you have to consult these manuals to understand what's going on in a lot of cases. And they try to give you a lot of test scenarios or kind of example scenarios and label the rules, right? And we talked about the .1 and .2 rules that are usually the width and spacing. Here you have some of the other more complex rules, right? Here you have poly.4, spacing of poly on field to diffusion. So what is field? That means where we don't have a transistor. There's that thick oxide where we're not going to have a transistor. And it has to be 0.075 to make sure we don't have the overlap. Or here we have, ignore tap for now, ignore tap, extension of diffusion beyond poly. This is actually the opposite direction that I showed here. I showed the poly extension among diffusion. There's also a rule going the other direction here. You can kind of see it. Bad green. Right? There's also a minimum extension that way. And that's what that rule is saying. Now, when I took the class, processes were simpler. We used to draw lots of layout. You ended up learning the common rules. But in general, there's the DRC tool, the design rule checking tool that can check all of these. The problem with modern design technologies is these rules have gone from 20 pages to like 900 page manuals of all the different layers and all the different exceptions and so on. I don't know of anyone that knows all of those rules. You can also have problems then where the DRC tool may not quite match some corner cases of the design rule manual, because some designer has to implement, or some tool person has to set up that tool to run, and they may forget a check. Actually, one check came up in Skywater. Remember I mentioned Metal 1 pin and Metal 1 drawing? Well, it turns out with Skywater, they're different than any other technology where I lied when I said that all those get unioned. They do on most technologies. In Skywater, if you draw M1.pin, it actually does not translate to metal on the mask. So you have to have M1.pin and a Metal 1.drawing to actually have something on the mask. This actually made a bunch of people have designs that didn't work the first time. That's an extreme situation if they used masks in a weird way. But that's an example of they could have had stuff in the design rule manual that someone didn't check in the layout, and there was a mismatch. Let's see, here I have another example that's a very common interlayer rule, where here, this is metal material on the outside here. So this is, say, metal 1. And this in here is your M-con. So this is a contact between metal 1 and polysilicon. They're going down layer. A via 1 would be the one going up to metal 2. And what this says is, I talked about extension of poly and diffusion before. Here you have to have a surrounding rule, where you want this metal 1 to surround the contact on all sides by some amount. Depending on the process, it may be symmetric, where you need a minimum kind of overlap on all the sides, or you could have an asymmetric surrounding. Like in 45 nanometer technologies, you will typically have, if you have metal 1 like this, your contact, let me draw it in black, can be like this, or this would also be valid. This is it must extend so much in either the X or Y direction, and it's okay. Where in Sky 130 here, it's metal 1.4, so the M-con must be enclosed by metal 1 by at least 0.03, and M1.5, M-con must be enclosed by metal 1 on one of two adjacent sides by at least. So it's the one I showed up there is basically 0 on one side is okay, and you have to have something on the other. This is something between that. It can be 0.03 on one side and 0.06 on two other opposite sides. So, right? It's different rules depending on the direction. This is what I mean by these rules can get kind of complicated, right? Older technologies used to be just, 0.06 on all the sides or something. But they do this to let you pack more things in, right? If you can make sure that it overlaps at least on two sides, the connection will be good enough that they can ensure that it's manufactured, but then you can pack more stuff in there. So that's why they made the rule that way. You know, if you can fit things in, it's better. Now, here's kind of a full example. This is generally from the book and kind of a lot of lecture sets of that 12-step CMOS process and how a layout of masks corresponds to the 3D view. I will guarantee some of the homework problems I give you are here's a layout, take a cross-section, draw the layout view. This is something I guarantee I will ask you on the exams. I could even go backwards and say, here's a cross-section, what does the layout look like? But you have to be able to translate not the absolute dimensions. We're looking at the relative connection of things. Because as a designer, you have to understand what's connected to what and what forms a transistor and what doesn't and so on. Now, in the class when I took it, you had to do lots of layout. When I started teaching the class, I made people do lots of layout. I think a better usage of your time now is to be able to recognize the layout, to see patterns, because you're going to have to recognize when there are errors. You know, a lot of times you don't actually fix the errors by hand anymore. you'll reconfigure the tool to prevent an error from happening. Or you'll recognize, oh, there's a DRC error in my library cell. I have to talk to the library vendor. They have to fix it. Or I have a routing error when I placed and routed my design. I need to fix the routing, but I'm not going to edit it by hand. I'm going to rerun the tool. So unless you're an analog designer or designing some custom piece in certain ways, you're generally not going to create the layout from scratch. Or if you're creating the cell library, you might do it like this. Okay, so here you can see this is basically, this A corresponds to this A, and this A prime corresponds to this A prime, right? So we're doing a cross section through that middle there. And the first thing to notice is that is an inverter. It's the same inverter essentially we saw before, except we actually have the gate connected, right? Remember the gate was not connected between here and here before? Because you can see it's connected in polysilicon, which is not in the cross section, right? Kind of that upside down N shape is what connects it. So it is electrically connected by the polysilicon to form the inverter. And you can see the yellow shape on the right is the well, over here. And that corresponds to this yellow down here. This active area corresponds to this mask right here. This area right here corresponds to this right here. You can see these vias, right? There's two vias right here. You can see them side by side right here. And that cut line goes right through the middle of them. What else? You can also see that there is a connection between this source and drain, and so you can see that it is this connection right here. Question?
How can you tell they're connected?
How is what?
How can you tell that like those two gray areas are connected?
Which gray areas? The
So in the middle, like between the source and drain.
Oh, so this, you mean this and this? How? So this right here is the contact. So this dark blue is the metal. And in this case, it's drawing the contact as this color plus kind of a stippled metal. And what that is that's trying to show, how do I want to describe it right now? So depending on how you do layout, you could either draw metal, a via or contact, and then another shape. But when two shapes overlap, they'll frequently change color in the display. And so what's happening here is this is saying, oh, I have diffusion overlapping with metal. I'm going to stipple the colors together to try to make it a green and blue combination. Most layout tools actually don't do that now. This is something they would do more in the 80s, 90s with Magic, which is a VLSI tool that's open source. But in general now, they will not make them like that. So now you'll typically see that it'll have a layering, and if something's on top of something, it'll obstruct what's below it. Now, how do you know what's below it? Well, that's a good question too. We can go back here. All of the tools have a set of things you can use right here. This says if I want to set layers to visible or selectable. AV is all visible, NV is not visible. And so you can either select things and say not visible. It turns them off. Or you can say selectable, select all these layers, and so then when I drag in the layout, I don't select certain layers. I only select the ones that are selectable. So that's a way to deal with the 3D. We see the same thing in these tools, except they shaded it. I think the boundary is there not visible. That's why it's a different color. But all these other ones are visible in the layout. And I forget how they designated selectable in this, but there's a way to do that. I think it does something on the side here for everything that's not selectable. So when I do the demo, I'm going to basically show you how to do that to see what is above and below other things. Yeah, so another TLDR is this is an old layout from an old book with an old tool. So that's something you generally won't see as much of these days. But it's still a good diagram. Here's another one from a different book. Same idea, different, showing it vertically and the different side. It's kind of a cartoon layout still. But basically the same thing, except it's not connecting. There's only one via on each of the top and bottoms, and it's connected a little differently there. Now, this one, though, what we can do is see how each of those steps in the manufacturing process have the mask go to the layout. So, for example, we have the mask on the left, and then we have the processing step on the right. So remember, we start with the substrate, p-type. We want to put in a p well or n well. In this case, it's actually a p well we're putting in. The n well will be on the top. And so what we do is we grow an oxide, we expose it, and we do the implantation to create this well here with this shape of mask here. And again, we're looking at the cross-section through the middle of this thing. Now, this is actually a N substrate on a P well process, just to be different than the other one, to be a little annoying. There are both of them. Here we now have the active mask that says where we want transistors. So this is where we'll have field oxide everywhere but these areas. This is where we don't want the thick oxide to insulate the devices from the first layers of metal. Or this is the areas where if we put poly in them, they will generally form transistors. So here we can do the two masks. We grow an oxide and we etch it away for these both P and N shapes. And then we grow the oxide where those devices are. Then we can actually put the poly on there. So again, we deposit poly everywhere, and then we're going to etch it away where it's not. Right? So we deposited the teal poly every place, and then this forms the shape of where we don't want it. Remember, we're looking at the cross-section here, so you only see this little segment. You're kind of missing this entire U because it's coming out from the board. And then the P plus select in this case. So this is where we want to do the source drain around the top device here. Then the N plus select mask, which would do the same thing to put the wells, the source and drain in for the bottom device. The green down here. And now this mask is going to do, two layers that are specific to SkyWater. L-icon, which is, Li is the first metal layer. It's below metal 1, but it's the local interconnect layer. So this is a contact between the source and drain to the source and drain. Or if we wanted to make a contact to the poly, this would be on the same mask, but we'd have another mask around the shape. That's the NPC. It's the nitride poly cut mask. So this is basically two masks. You can either have two masks, one to create these and one to create contacts to poly, or what this does is says, I have one mask with all of my contacts, and I'm going to say which ones are to poly. Again, the combination of these can change. The combination of the layers can get converted to masks in different ways, is the point of this. It's okay if you don't quite understand that part for now. And then we can go up to metal 1, and again, adding vias and so on. Now, how does this look like real layouts? Well, here's an example of an inverter 1 layout. Those were cartoon layouts to show cross-sections and stuff. They were bad layouts. You know, why are they bad? Well, that poly and kind of that U shape, no one does that, other than in textbooks to show how you do layout. The way you always see it is something on the right. Unfortunately, the shading is a little bad in this, but I'll highlight it a little bit. You can see that the polysilicon shape is like this. Okay? And the thing to note is that the two transistors, instead of being sideways like in the other layout, they're rotated so that the poly is vertical. And that way, if you want two transistors in an inverter to be connected, you just connect them with poly, straight poly, right? There's this connection from this one down to this one, right there. Very easy to connect. You align the P and the N that get connected together. The gate gets connected together above and below each other. And then over here on the left, let me draw it in this color. This is an L icon. It's kind of hard to see there. That connects up to Li. And then if I draw in another color, maybe this black is then the Li layer, or that kind of other color. So what this is this basically took that polysilicon and connected it to that square up to the first metal interconnect, that local interconnect layer, because that's the pin where you connect to this inverter, right? Now on the output of this thing, what you can see is there's another set of Li. This is easy. Oops. This right here is also Li. And you can also see the Li con layers here, right? Here's 3 Li cons going down to the source or drain of that transistor, the drain of that transistor. And then you can see it's shown in kind of a red, but like this right here, I'm going to kind of draw it like this, and here, I'm drawing them in that color, but that is basically a pin. So this is the Li dot pin layer. It's a red. I don't know why they made it red. It's distinguishable from the other color, but that's where the output of the gate is. Now, yeah, question.
So why are there two chunks for the output?
Why are there two of the vias, or the two pins, you're saying?
Yeah.
I'll talk about that when we do cell design, but it's multiple places you could connect to. I'll talk about this when we talk about cell design. Connecting to either one would connect to the output. Now, the other thing to notice here is you can then see the purple shape, or the blue. Up here in the top, this is VDD. And then down here in the bottom, this is ground. And you can see also there's a little bit of connectivity on the Li layer to the VDD and ground as well, right here. So we're going to go over layouts a bit more. I'm going to give a demo, but this is kind of a general example of how real layouts are done. So digging in really fast, really dirty, and get to see some stuff. K-layout's kind of cool because you can also see some 3D views. Now, this isn't the perfect 3D view because I actually set up the color palette and the Z dimension. I didn't do it perfectly. There's a couple somewhat mistakes. But you can basically take that exact layout that I just showed and you can see it in the 3D viewer, right? This is that exact layout right here with two different views, right? You can see the two Li con. This is the Li con to the source drain. This is the Li con to the poly. This doesn't show the pins, right? You asked me about the two pins on the output. They're not here because they're not a shape. Right? Those would have been somewhere in this area, but they're not there. What else about this? Yeah. So that's where I have, when you do the tool setup, you should be able to do a 2.5D view like this of layouts to help you with some of the homework problems. It's a little tricky to set up and get running. You need 3D acceleration enabled, which is kind of a pain in the ass, but it's possible. In general, though, you don't do this in commercial tools. Most commercial tools actually don't have this feature because most designers don't view it this way. You just know that these things are connected. You can't do this in Cadence Virtuoso. So, now, one thing to kind of note, so that's a simple inverter. One thing that's frequently done in cell libraries to help make compact layouts and is to basically do what's called well and diffusion merging. So in this top example here, I have two transistors, right? I have a well with one transistor on the left. I have a well with another transistor on the right. And let's say I want to connect the source and drain of those two transistors together. Well, how do I do that? Well, I go up through a contact. I go to metal. Then I want to connect the metal together, right? Well, what sort of design rules do I have here that I have to follow? Well, there's a number of them. I had a design rule here that was an n-well, I forget it, .2a. That was an n-well to another separate n-well of a different, right? We had the notching rule, and then the different n-well rule. That's a spacing that's actually very big in most processes. Then I'm going to actually have an n-well beyond diffusion rule. I'm going to have a minimum extension beyond poly rule. I'm going to have a minimum width rule, and so on. I'm going to have these same rules over here. And so this is basically as close as I can put these things together. By the way, there will also be a rule in here that's how far this contact has to be away from the poly. And then how much this surrounding area of the diffusion around that contact. So and then the width of the contact. So there's basically rules here as well. Which one is bigger determines how much that kind of wing of the transistor is, right? Now, one thing I can do is, rather than putting these in their own well, is just put them in the same well. Then I don't need any well spacing, and I get what's down here, which is, now I just have a diffusion spacing rule, which is diffusion.2 something. I saved the distance of nwell.2a. Didn't change the behavior at all. Well, now I have this diffusion.2. I still have these other things. Well, what if I just connect the diffusion together? Remember, this one over here, let's say it's going to be P+. This one over here is going to be P+. I can just merge those together and have one P+ region that's connected. So that's what I can do here. Now I have basically my spacing rule is the width of this contact and then the spacing of the contact to the poly. Same function. Now, what if I don't need to connect to this electrically? What if it just needs to connect this transistor and this transistor? I can get rid of this metal and this contact. Now, I have one design rule here, which is actually just poly to poly spacing over diffusion. Each one of these things had the same exact electrical function, but that one on the bottom right is like half the width of the one on the top left. This is an example of kind of efficient layout can have significant impacts on your area. We see this all the time within standard cells. If you make a series connection of a NAND gate, it's going to be like that. Or a NOR gate, it'll be like that. However, it's still going to typically have the vertical polys are going to line up to make those easy to route. So what does that look like? Well, here's two examples of a NAND gate. The left one is actually in a ST Microelectronics, I forget what technology node. And then the one on the right is SkyWater. Now the reason I showed the one on ST Micro is that one's old enough that they had crazy design rules, and I just want to highlight it. Like, if you look right here, this has 45-degree poly. Right? It's not vertical, it's actually angled. You can't do that anymore. Same thing in these other spots as well. in general, that didn't save much area, but it let you put these transistors down here closer together because they shared diffusion. But then your ones up here still had to be kind of far apart. But then you did this angle to make space for the contact here, and so on. It made it really complicated and didn't save much. So that's why they don't do it. And it's also hard to print. So now on the right, you basically see an example of a 2-input cell from SkyWater. This is much more traditional where you have kind of straight vertical stuff. But the thing to notice is they all have the VDD and ground have these kind of footer things, which these are going to let you put them in rows later and easily connect together the VDD and ground. What else do I want to highlight about this? But you can also see, again, the color palettes are similar. The layers generally have the same function. Most of that is going to be the same from technology to technology. All right. We only have 5 minutes. So what I'm going to do is probably start with a demo of K-Layout next lecture and show you that. If you want to get set up on the demo yourself, here's the link to the chip tutorials. And you can install K-Layout and download the technology information and load these designs like this. We're going to post homework 2, which you're going to have to do some stuff with layouts. So I know homework 1's not due yet, but we're going to post that soon just to give people a head start. Okay?
I'm Harry from like Slack.
Oh, yeah. You got in on the wait list? That Harry? Oh, okay.
There's another one?
Yeah. Oh, there's a Hari, H-A-R-I. You're H-A-R-R-Y.
Yeah,
Okay.
the one about like editing PDFs. I was wondering if you have overly like LaTeX files for those PDFs.
I do. I don't really want to share them though. Yeah, I don't think that would help you really though, because you'd then reformat stuff and it wouldn't line up with our grading.
I guess that's true. Yeah.
Yeah.